Hi science students, today's lesson is about mixtures and solutions. This is the beginning of our solubility unit. Mixtures and solutions are similar but not the same thing. So we're going to begin with mixtures and then we'll go into solutions. You will need a sheet of paper that you can write on both sides of. So you're going to write about mixtures on the front and about solutions on the back. So you want to make sure that you have enough room to write on both sides. You also want to make sure that you have a pen or a pencil. If you want to use multiple colors, you can, but that's certainly not a requirement. Let's go ahead and dive in. So we're going to start with mixtures. On your paper, you're going to write down mixtures, but then you're going to write down the names of the two types of mixtures that we're going to discuss. Heterogeneous mixtures and homogeneous mixtures. Draw two little arrows to separate two big columns, and we'll start with heterogeneous. Feel free to pause the video at any point if you need to, if I'm moving too quickly. So, heterogeneous mixtures, this prefix hetero, we know is going to mean things that are different from one another. They're going to be inconsistently sized. So heterogeneous mixtures are going to be a combination of substances that are not uniform, meaning that they're not the same size, they're not evenly dispersed, and they're easily distinguished. I can tell that that is one particle and that is something totally different. They're not going to be easy to blend in together. It's going to be easy to tell that they're two separate things. So some examples of that are going to be down here. I've got sand and water. Sand is not going to mix with the water and become dissolved. Instead, it's all going to sink to the bottom. So I've got sand and water as an example. I can easily distinguish the sand from the water. And the same with this raisin toast. I'm easily able to tell that's a raisin or that's a piece of bread. And so both of these are really good examples of heterogeneous mixtures. Homogeneous mixtures are going to be similar but not the same. They're going to be combinations of substances, but they're basically going to be the opposite of a heterogeneous mixture. Homogeneous mixtures are going to be able to be uniform, where everything is mixed evenly together, and they're not going to be able to be easily distinguished. So when I look at a homogeneous mixture, I can't tell that that's one particle and that's a different one. I can only see the mixture combined evenly. So an example of that would be salt water. Salt water is going to evenly mix together, and all of the molecules of salt are going to attach to molecules of water, making them seem like they have disappeared. Solutions, which we'll go into in just a second, are going to be homogeneous mixtures, where they're mixing and they're going to be uniform. They're not going to be able to easily distinguish the parts like I can with heterogeneous mixtures. If you need to pause the video to make sure you have everything on your paper that's the same as mine, please do that. I'm going to go ahead and move forward. Flip your paper over to the back. When you do that, we're going to go, instead of the same direction we were going, we're going to go up and down now. And on the back of the paper, we're going to be talking about solutions. So write solutions at the top of the paper, and we're going to be going vertically now instead of horizontally. So solutions, like mixtures, are going to be combinations of substances. Typically, it's going to be a liquid and a solid being mixed together, but solutions can vary in how much is being dissolved. So solutions are composed of a solute, which is going to be whatever the substance is that I'm trying to dissolve. Salt, sugar, chalk, whatever. The solute is going to be the thing that you are dissolving. And a solvent is going to be the liquid, typically, that is doing the dissolving. So if I'm mixing salt into water, salt is my solute, and water is my solvent. Again, if you need to pause at any point because I'm going too quickly, please do that. So solubility is what we talk about when we're discussing solutions. We talk about, is it soluble? And we looked at that when we did our last PBL. We were talking about if something is soluble. So you've already practiced with this a little bit, but make sure you have the definition of solubility. Solubility is the ability of a solvent to dissolve a solute. And like I said previously, that can vary in the amount of solute being put in, that can vary in the amount of solvent being able to actually dissolve all of those particles of the solute. So there are 3 different types of solutions. They can be unsaturated, they can be saturated, or they can be super saturated. So we're going to start with unsaturated. Let me go like this so you can see the whole thing. An unsaturated solution is going to be one that has a solute that's been dissolved less than the maximum. So meaning I'm pouring in some, say salt, we'll say that this is salt water. I'm pouring in some salt, but I could still put more in there before it reaches the maximum amount that that water can hold. So unsaturated means that I've put in some solute, but there's less than what the maximum amount of solvent can hold. The water could hold more salt than what's in there. So that's what unsaturated is. Saturated is going to be a solution where the maximum amount of solute has been put in. I can't put any more salt into the water. It's evenly dispersed. The water is holding as much salt as it can. And all that means is that if I were to continue to add, the salt's going to begin to pool at the bottom rather than actually mixing and attaching to those water molecules. So saturated solutions are going to be the maximum amount of solute that can go into the solvent and still mix. If I've put more than what can still mix with the water, I've created a supersaturated solution. So a supersaturated solution is where there's going to be more than the maximum amount of solute. And I tried to draw a little pile of salt beginning to form at the bottom. Supersaturated solutions often will form crystals at the bottom from that pooling of the solute, pooling down at the bottom, piling up, and creating some crystals. So I want to show you an example of that, and I'm going to let you watch it, and then I'll talk about what you should be seeing and how that is an example of a supersaturated solution. If you need to pause the video to write this stuff down, please do that, but I'm going to go forward and play this video for you. So in this video, what you're going to be seeing is some liquid water in this Erlenmeyer flask, and he's going to put in some sodium acetate. This is a solid substance that he's going to drop into the water. And as he does this, he's going to notice that there's some agitation. It's going to change in temperature, and there's going to be a lot of movement within the water. So continue to watch, but he's about to add in some sodium acetate here. And you can kind of see it dispersing into the water. It's trying to saturate, but there's too much substance. So what you're going to notice is that it's beginning to fill the whole space, and it's actually solidifying. It's forming a crystal because it's so super saturated, so overly saturated that the temperature changes. It becomes warmer, and it also becomes a solid. So it no longer is liquid water. It's changing form because it's so super saturated. It forms those crystals, because there was way too much sodium acetate in comparison to how much water was present in the flask. So that's everything we have to talk about with mixtures and solutions today. If you have any questions beyond this, feel free to post them on eClass or to ask them while we're together in class today. Please have a really great day, stay safe, and I'll see you later. Bye.